For centuries, humans have harbored secrets. These secrets, whispered in dark corners or encoded in cryptic messages, have shaped history. Cryptography, the art of secure communication, has always played a crucial role. It is the shield protecting our information in an increasingly interconnected world. From ancient ciphers to modern algorithms, cryptography has evolved dramatically. One such marvel of modern cryptography is the RSA algorithm. RSA stands for Rivest Shamir Adleman, named after its inventors. This algorithm is a cornerstone of modern digital security. It underpins everything from online banking to secure messaging. Understanding RSA means grasping the fundamental principles that keep our digital lives secure. RSA belongs to a class of crypto systems called public key cryptography. Unlike symmetric key systems, which use the same key for encryption and decryption, RSA employs two keys, a public key and a private key. The public key, as the name suggests, can be given to anyone. It is used to encrypt messages, transforming them into an unreadable format. The private key, however, is kept secret. It is the only key capable of decrypting messages that were encrypted using its corresponding public key. This system is analogous to a locked mailbox with two keys. Anyone can drop a letter in the mailbox using the public key, the open slot. Only the owner, with the private key, the unique mailbox key, can retrieve and read the messages inside. The ingenuity of RSA lies in its mathematical foundation. It leverages the properties of prime numbers and modular arithmetic. At its heart is the near impossible task of factoring large numbers. To generate the public and private keys, one must first choose two large prime numbers, traditionally denoted as P and Q. The product of these primes, n, and equals P times Q, becomes part of the public key. Another crucial component is the totient of n, denoted as pun. Calculating per n is straightforward if you know P and Q. The security of RSA hinges on the fact that finding n without knowing the prime factors of n is computationally very difficult. Section 4. Cracking the code. A step-by-step RSA example. Let's illustrate how RSA works with a simplified example. Imagine we choose the prime numbers 11 and 13. We calculate and as 11 times 13, which equals 143. The totient, phi of n, is calculated as 11 minus 1 times 13 minus 1, which equals 120. We then choose a public key exponent, e, which must be relatively prime to phi of n. Let's choose e as 7. The private key exponent, d, is calculated such that e times d mod phi of n equals 1. In this case, d equals 103. To encrypt a message, represented as a number m, let's say m is 9, we use the public key, ne, and the formula c equals m raised to the power of e mod n. Here, c represents the cipher text. In our case, c equals 9 raised to the power of 7 mod 143, which equals 48. To decrypt, we use the private key, nd, and the formula m equals c raised to the power of d mod n. This gives us m equals 48 raised to the power of 103 mod 143, successfully recovering the original message of 9. Section 5. Real-world applications of RSA. RSA's impact on our digitally driven world is profound. Every time you make an online purchase, check your bank account, or send a secure email, RSA is likely working behind the scenes. It forms the bedrock of secure communication protocols like TLS, SSL, ensuring that data transmitted over the internet remains confidential. Beyond these everyday examples, RSA plays a critical role in digital signatures, verifying the authenticity and integrity of digital documents and software. Governments use it to secure classified information, and businesses rely on it for secure internal communications. Section 6. The enduring importance of RSA. Despite the emergence of newer cryptographic algorithms, RSA remains a cornerstone of digital security. Its strength lies in its well-established mathematical foundation and its proven track record. As technology advances, so too do the challenges to cybersecurity. Quantum computing, for instance, poses a potential threat to RSA's long-term viability. However, the cryptographic community is actively researching and developing new algorithms to counter these emerging threats. RSA's legacy will undoubtedly continue to inspire and influence the future of cryptography, ensuring that our digital world remains secure.